Yeah, thank you for the kind introduction, and I want to thank the organizers for inviting me to give this talk. It's my pleasure to be here in Chongqing for the very first time in my life. Today I'm going to talk to you about materials design at scale with universal machine learning models and big data. So my name is Xueping Ong, and of course I know that some people have difficulty pronouncing it, and since I'm in China, I might as well share that my Chinese name is actually Wang Xueping. So my ancestors are from Fujian, and the reason why my name is spelled this way is because that's the Minnanhua's translation, okay? Now, I'm a professor in the Department of Nano and Chemical Engineering at UCSD. So I lead what is called the Materials Virtual Lab, and we are a pure computational materials lab, focusing on the application of high-throughput DFT calculations as well as machine learning to accelerate materials design, okay? Now, at this conference, I don't think I need to convince you that we are now in the age of in silico materials design. In other words, we are now able to not just use experimental laboratories to discover new materials, but also we are able to use computers to accelerate the discovery of materials, right? Now, this actually really started a very long time ago with the discovery of quantum mechanics. So there's this very famous quote by Paul Dirac, who said that, well, the underlying physical laws that govern most of physics and all of chemistry are already completely known in 1929, okay? And of course, when he said that, he was referring to the Schrödinger equation over here, okay? Now, he also was a bit pessimistic about its application. He actually said that, well, the solution to these equations are actually too difficult, and we can't actually solve them, right? But of course, now with very, very powerful computers, we can now actually solve the Schrödinger equation to some extent. And by solving the Schrödinger equation in the computers, we can now already derive a lot of material properties just from computation alone without ever having to step in the lab, okay? Now, the good thing about using computers to solve the equations of physics is, of course, that with more computers, we are able to scale up our computations to basically get more material properties, or we can also perform computations on more materials, okay? So that's the underlying concept behind the Materials Genome Initiative, which was started back in 2011 by former President Obama, okay? So one of the big projects under the Materials Genome Initiative is known as the Materials Project. We call ourselves the Google for Materials. So this was started in 2012 by Christine Pearson together with Gert Sieder and myself and a few other people. And basically, this is an open science project to make the properties of all known materials publicly available to all researchers, including researchers like yourself, to accelerate materials innovation, okay? So today, we already have about 150,000 materials in the Materials Project, and a lot of these materials also have properties computed, right? So the natural question, whenever you see statistics like this, is why can't we just keep doing DFT calculations or ab initio calculations, right? Why do we need machine learning? Why can't we just compute everything, right? And the reason is very simple, right? Ab initio calculations, such as those that are based on solving the Schrödinger equation, do not scale, okay? So the way that I show you this is basically looking at the data history of the Materials Project itself. So as I mentioned, Materials Project started back in 2012. We are now close to 2023. And what you notice is that through the years, we have steadily increased the amount of data in the Materials Project, both in terms of structures as well as in terms of the properties that are in the Materials Project itself, right? And what you see immediately is that we have sort of stagnated in the past 3 to 4 years or so. So we have been at about 130 to 150,000 materials for the past 3 to 4 years, right? And even worse, there are a lot of properties that we are computing very, very slowly, right? So, for example, when you want to design a new structural material, you will want to know its mechanical properties. But for properties such as elastic constants, we have a much smaller data set, right? So we only have about 10,000 or so elastic constants computed, right? And this pace of computation is definitely not enough to accelerate materials innovation, right? Because, as we all know, the materials design space is combinatorial, right? So nowadays we are exploring materials such as high entropy alloy, where we basically throw a lot of different elements together to form new alloys with better properties. We are also interested in complex material systems, right? So basically materials that are formed by the interfaces between two different crystals. We are also interested in polycrystalline materials, right? So what this means is basically that just using ab initio computations alone, we are not only unable to scale to the number of materials computations that we need, we are also unable to scale to the size of the simulation that we need, okay? But there is actually good news, right? The good news is that once we actually have a good amount of data, and we do have that today, we can now begin to apply machine learning techniques to basically learn from the data that we already have, and then use those machine learning models to basically predict the properties of all the materials that we haven't looked at, okay? And that is the underlying concept, right? So what is machine learning? Machine learning is the scientific study of algorithms and statistical models that basically learn to perform some specific tasks without the use of explicit instructions and relying on patterns and inference instead. In other words, for machine learning algorithm, basically what you give it is data. Typically when we talk about this in material science, we refer to basically structure the data on one as the input and the material property as the output, right? And what you hope is that given enough data, the machine learning algorithm actually learns the relationship between the input and output, right? And of course, machine learning is a very big topic nowadays everywhere, right? So every time we talk about things like self-driving cars, which I know is a big thing in China, or even weather forecasts, or even something like playing Go, all those are powered by machine learning algorithms, right? Now, the type of machine learning algorithm that my group likes to work with is what I call graphs, okay? So it turns out that graphs are a very universal representation for materials, right? So you can imagine that the atoms are the nodes in the graph, and the bonds between the atoms are basically the edges in the graph, right? So a number of years ago, we actually developed this architecture called the Materials Graph Network, or what is called MagNet. This is a very generic and flexible representation that works across either molecules or crystals or everything in between, okay? And one unique feature about the MagNet models that we developed is this global state variable that actually allows us to introduce more greater expressive power and flexibility in handling data types and different types of models, okay? Now, basically in this kind of graphs, you basically do what is called message passing, okay? So you use neural networks to pass information from the atoms to the bonds to the atoms, and also the bonds and atoms to the global state, right? And once you have enough of those message passing layers, what you get is basically a graph neural network algorithm, okay? And it turns out that this kind of graph-based machine learning models are actually extremely powerful, right? So today, when we talk about the best performing machine learning models for predicting a lot of different material properties, by and large, the state-of-the-art are graph neural network-based models, okay? So this statistics that I show you here is already a few years old. Nowadays, we, of course, have slightly improved models. I wouldn't say that the improvements are a lot more than what we have achieved back in 2019. But we can already predict things like the formation energy of crystals to within about 28 milli-electron volt per atom or so, okay? We can predict the band gap of materials to within about 0.33 electron volts. We can also make models that can predict things like the bulk and shear modulus of materials, right? Just to illustrate what that 28 milli-electron volt per atom mean, okay? So there's this work that was done a few years ago by Professor Wenhao San from the University of Michigan. And he basically showed that out of all the crystals in the ICSD, about 80 to 90% of those materials fall within 100 milli-electron volt per atom below the convex, above the convex hull, right? And what this means is that once we actually get to an accuracy of about 28 milli-electron volt per atom or so, that is much lower than the limit for synthesizable materials, right? So what this means is basically today we can already predict to some good degree of likelihood whether a material is likely to be synthesized or not before we actually try to make it in the lab, okay? Now, I also want to highlight that these machine learning models are not really just pure black box models. So I know a lot of times machine learning models get a bad rap. People always say, well, we don't know how they are actually making the predictions, or we do not know whether they learn anything useful. They actually do, okay? So for instance, we can take the elemental embedding vectors from our materials graph network models, and we can plot the correlations between the elemental embedding vectors for all the different elements. And what you see is that essentially the magnet models actually learn the periodic table of the elements, right? So for instance, all the alkaline metals and all the alkaline earth metals are basically clustered together. They have very high correlation with one another. So these are elements that we know are chemically similar, right? And you can also see this in what is called a TSNE plot, where you can see basically all the different groups of the periodic table are actually clustered together within this TSNE plot, okay? Now, given that magnet models actually can learn chemistry, the question then is, can we exploit this chemistry that is learned to actually make better use of our data, right? So this is what I call maximizing the return on data, right? So we all know as material scientists that a lot of times we don't have enough data, right? Or we don't have enough high quality data. There's a very typical truism, right? The higher the value of the data, the more expensive it is to get it, right? So for instance, we can actually get the bandgap of crystals using what is called a PBE functional in DFT calculations. And this is very cheap, right? We can do this for a lot of materials. And just going to the materials project, you can get about 52,000 band gaps for different crystals, right? Now, we can of course also do more expensive calculations, so things like using a hybrid functional like the HSE functional. And these band gaps are a lot more accurate, but they are also a lot more expensive to calculate, right? So the data set size for something like a HSE functional is about 6,000. So almost one order of magnitude smaller, right? And of course, the most expensive technique to get a band gap is basically to try to make the material and measure it in the lab, right? So the experimental data set is even smaller than the HSE and PBE functional. Now, this is where we can leverage on the unique architecture of the magnet models to actually use all the data that we have on hand, right? So we develop what is called a multi-fidelity magnet model, where we basically use the global state variable to indicate what kind of data it is, right? Is it a PBE calculator band gap? Is it a HSE band gap? Or is it an experimental band gap, right? And other than that, the architecture remains the same. So we are reusing the learned chemistry from our magnet models, right? And what this allows us to do is that we can take all the data and fit just one single model to predict any kind of band gap, not just the PBE band gap, right? Just to show you that it works, so for instance, if we just build magnet models to each of the data sets by themselves, you can see that we can get fairly low errors on the PBE data, but our errors on things like the HSE band gap and the experimental band gaps are almost 2 times bigger, right? And the reason is really because the data set size for these 2 data sets are much smaller, right? Now, by using a multi-fidelity approach, in other words, we combine all the data together, we can get a 40 to 50% improvement in the prediction of our high-value band gap information. So HSE band gaps and experimental band gaps, we get this 40 to 50% improvement in the prediction accuracy without actually having to measure any more experimental band gaps or having to calculate more HSC band gaps, okay? So in other words, we are getting something for nothing just by leveraging on the chemistry that is learned in our materials graph network models, okay? All right, so hopefully I've convinced you that today we can actually build machine learning models that can predict a lot of material properties to some degree of accuracy if given the structure, but there are limitations to this approach, right? So the very, very first limitation is, of course, you first need an input structure to give the materials graph network model, right? And usually the way that you get an input structure is to do a DFT calculation. So that kind of defeats the purpose of using a machine learning model, right? So you still need to do a expensive DFT calculation to get the structure. The other bigger problem is that there are some properties that are emergent or they do not actually have a very continuous relationship with structure or composition, right? So one of the big areas that I work on is lithium-ion batteries, right? And we work on solid electrolytes for all solid-state lithium-ion batteries. And one of the most famous solid electrolyte is called the LLZO, or lithium lanthanum zirconium oxygen garnet, okay? And this is actually an experimental result which shows you that just by very, very small changes in the composition of LLZO, if you just dope it with a little bit of aluminum, you actually can get very, very large changes in the ionic conductivity of LLZO, right? You can get a 2 orders of magnitude increase or decrease in the ionic conductivity just with a little bit of aluminum or with a phase change from the tetragonal phase to the cubic phase, right? And this kind of 2 orders of magnitude change or very discontinuous change is very, very hard for machine learning models to model properly, okay? So let me first show you how we can actually solve the first problem, right? If we want to get an input structure, can we do it without DFT calculation? And the answer is yes, right? We can actually combine Bayesian optimization with our magnet models to basically relax crystal structures without using DFT calculations, okay? So this was basically the approach that we developed in this work. There's a collaboration with Professor Jian Luo of UCSD, where we basically use magnet as an energy calculator, and we basically relax the crystal to the lowest energy form without using any DFT, okay? Now, to show you that this actually works, I'm going to show you one of the prime examples where we actually managed to go from a machine learning model prediction all the way to an experimental synthesis of a completely novel material, right? So the target application is actually ultra incompressible materials. So what we did was to basically take ternary prototypes, about 5,000 ternary prototypes, and we basically put in a bunch of different elements, okay, molybdenum, tungsten, osmium, and rhenium, as well as boron and carbon. We generated about 400,000 potential crystal structures, and then we use this Bayesian optimization process to basically relax them, and then use a machine learning model to predict things like its stability, the bulk modulus and shear modulus, and then we do a preliminary screening, which then results in about 1,000 materials, which we then use DFT calculations to confirm. And finally, our experimental collaborator actually went ahead to make it in the lab, okay? And I'm showing you just 2 examples of the materials that they found. So there's this rhenium tungsten boride and this moly tungsten carbide. They are both completely new materials. In other words, these are materials that no one has ever reported before. The measured XRD patterns are very, very close to what we predict from our computations, and the properties are also extremely close to what is predicted from our machine learning models as well as our DFT calculations, okay? So this work that was done by Yunxing Zhuo, who is actually in the audience today, okay? All right. Now, another way in which we can relax crystal structure is to basically develop what I call machine learning interdynamic potentials, okay? And this is actually one of the major success stories of machine learning in material science, okay? by today, it is a very, very well-established approach. The way that this works in general is that you take the local environment around each atom, you then convert it into a series of local environment fingerprints, and then you use a machine learning model to map the relationship between your potential energy surface, in other words, the energy and forces on each atom, to the local environment fingerprint, okay? So today there are a bunch of different architectures and models, but this is a very powerful development because once you actually have the potential energy surface, you can derive a lot of properties. You can relax your crystal structures, you can get finer energies and stability. You can also get, of course, derivatives of the energy, okay? So things like the mechanical properties, the phonons, and a lot of finite temperature properties as well. You can get things like molecular dynamics derived properties like ionic conductivity and diffusion, right? Now, even though this is a major success story for machine learning, there are a few limitations, right? When we talk about machine learning intolerant potentials, typically the ones that have been developed in the past, they have terms that grow combinatorially with the total number of elements. They also have to be custom fitted to every single system that you study. So in other words, you really cannot use them for large-scale material screening, right? So this was when my group actually had the idea of using graph-based machine learning models to develop a chemically scalable machine learning intolerant potential architecture, okay? So the architecture that we developed is what are called materials three-body graph networks, or M3GNet, okay? So this is basically the same architecture as the magnet models, except that we actually add three-body terms within the architecture, right? So the reason is to make it more expressive and more powerful in terms of modeling the local interactions between atoms, okay? Now, to train a universal intolerant potential that can cover the entire periodic table, we basically took all the data that we have in the materials project in terms of structural relaxations. So since 2012, the materials project has performed about 150,000 structural relaxations. That means that we have around 100,000 energies, 10 million forces or so, as well as 1 million stresses, and we can throw all this very, very large data set to actually fit one universal intolerant potential that can cover 89 elements of the periodic table, okay? So this is what we also call an AlphaFold for material science, right? So if you know, basically AlphaFold is this algorithm that was developed by Google DeepMind for predicting 3D protein structure, right? So here we develop a universal potential that can actually relax and get the structure for any material, okay? So just to show you that this universal potential actually works, okay, we can actually today get relaxed crystal structures that are within 1 to 5% of what you will actually get with DFT structural relaxations, okay? And this is almost near instant compared to DFT calculations. Once we are actually able to get structures that are within 1 to 2%, we can also calculate its energy and make stability predictions, right? And we can show that basically our stability predictions are almost in very good agreement with what you would get from DFT calculations, right? You can also get a lot of different properties from a universal potential. We can calculate things like what is the phonon dot center, okay? Again, you can see that the agreement between the DFT and the M3GNet derived phonon dot centers are in very good agreement. We can simulate things like the bulk modulus just from calculating the derivative of the energy with respect to displacements. We can even get ionic conductivity from MD simulations, okay? So this is an ionic conductivity of this solid electrolyte called Li3YCl6, and we can show that basically the conductivity that we get from our M3GNet simulations are very close to what you would get with ab initio molecular dynamics, okay? Now, if you are interested in playing around with the model, like all the models that we develop in my group, we always release all the models and data publicly on GitHub and in other public domain, okay? So we developed this library called the Materials Graph Library in collaboration with Intel. Today, it already has M3GNet and MagNet implemented. We are also implementing other machine learning potential formalisms, things like TensorNet, SO3Net, and ChargeNet as well. And it already has multi-GPU support. And since the publication of this work, there has been a lot of interest from the community. I'm, of course, the author of PyMatGen. That is widely used by a lot of you here. And we already integrated structural relaxations using M3GNet into PyMatGen. There's also a lot of software out there, companies out there that have integrated M3GNet into their commercial products as well, okay? Now, where can you use M3GNet? You can, in short, basically anywhere that you use DFT for, but you can actually get away with not DFT accuracy, okay? So for example, we can now expand the search space for new materials. So while in the past, maybe you would do DFT calculations on, say, 1,000 materials or 10,000 materials, you can now explore millions of materials, right, in one shot, rather than using DFT only, right? You can also sample more robust sampling spaces. I'm not going to talk too much about this. But I want to give you an example of how we are using M3GNet to actually search for new lithium-ion battery materials, okay? So as we know, in all solid-state batteries, the main component that we are interested in developing is the solid electrolyte that can conduct lithium ions between the cathode and anode. So whenever we want to design a solid electrolyte, there are a few properties that we are interested in. We are interested in is the phase stability, the electrochemical stability, the ionic conductivity, the electronic conductivity, and the mechanical properties, okay? Now, as it turns out, most of these properties, you can actually get it from just having knowledge of the potential energy surface, okay? So all these things in green, you can actually get it just from an M3GNet calculation. For the electronic conductivity, you can estimate it using, for example, a magnet bandgap model. And basically what we did was to generate about 31 million structures. We actually found that about 1.8 million of them have an E-hull of 0. In other words, they are predicted to be stable on the convex hull. We can calculate things like the electrochemical window. You can see that on the right here is basically what you get with M3GNet. On the left here is basically what you get with a DFT calculation. And you practically can't tell the difference between the M3GNet prediction and the DFT calculation, okay? So we can then calculate the conductivity as well, and we can, for example, identify regions where we actually find all the good lithium superionic conductors. And of course, you can see that there are a lot of dots here that have not been explored as lithium superionic conductors, okay? Now, since the publication of this work, there have been a few developments since, okay? So for example, there's this work from the CEDAR group. It's basically roughly the same concept, but they actually use local magnetic moments as a proxy for the oxidation state. So their model can actually deal with charge separation systems a bit better, okay? So this is called ChargeNet. And I'm sure a lot of you have heard last week's news where Google DeepMind actually announced that they discovered millions and millions of materials, that paper published in Nature, okay? And it's basically the same concept. It's this universal potential, roughly the same architecture. They do have, the data set size is much, much bigger because they have huge computing power resources that a lot of us don't have. But I want to caveat that no one here would be able to use it, okay? The data, the model, they are all not available to anyone. So the only way you can get it is to join Google, okay? So that's the current state of this model, okay? So I'm going to conclude. I just want to say that using graph-based machine learning models, we can actually build universal models for material science and materials design, okay? I want to also highlight that basically the use of machine learning all the way from machine learning to DFT to actual discovery is already a reality, right? I already showed you an example where we actually made that happen, right? And graph neural I also want, the final point that I want to make is that we are now primarily constrained by the quantity and accuracy of DFT data that we have, okay? And so what's next? In collaboration with the materials project, we are developing this initiative called MAPPAS, or Materials Potential Energy Surface, where we are going to develop an open data set of potential energy surface data, okay? So this is complete opposite from the Google data, right? We are not going to hide it. We are not going to keep it to ourselves and sell it. We are going to make that available to you, and it is going to come out, I would say, within the next few months or so, okay? We also need to develop models with better physics, right? Can we describe long-range charge transfer better? Can we develop models that incorporate symmetry and other physical constraints better, that allow the model to extrapolate better to unseen chemical spaces, okay? And finally, we also need better software, okay? So a lot of these models, they are fast, but they are not as fast as we would like them to be, all right? So we would like to be able to apply them to material systems containing millions of atoms, but today maybe we can apply them to systems that contain tens of thousands or hundreds of thousands of atoms, okay? Can we actually develop better parallelization and better software for doing this kind of materials computation, okay? And with that, I thank you, and if you are interested, this is the open access article. That's the QR code if you want to get it. This work was primarily done by Chi Chen, who is now quantum architect at Microsoft Research, and this work is of course funded by the Materials Project under the Department of Energy in the US, okay? And thank you.
Thank you so much for your very nice talk. Since this is a plenary lecture, we do not set time for the Q&A, and we just stop here and appreciate